The Moon is Earth's only natural satellite, and one of the most remarkable companions a planet can have. But before we continue, please make sure to subscribe and leave like for more sleepy science videos. Orbiting at an average distance of about 384,400 kilometers, it is close enough to dominate our night sky, yet far enough to maintain a sense of mystery. Its size is unusual in planetary terms. Relative to its host planet, the Moon is the largest satellite in the solar system, making it a significant player in Earth's stability and evolution. Beyond its physical presence, the Moon has been a silent witness to billions of years of history, from the birth of our planet to the rise of human civilization. It has shaped life on Earth through its gravitational influence, creating tides that affect ecosystems and possibly even the origin of life itself. For humans, the Moon has been a constant source of inspiration, guiding ancient navigators, structuring calendars, and embedding itself in myths and legends across cultures. In modern times, it became the first celestial body visited by humans, turning a distant dream into a tangible achievement. Far from being just a rock in space, the Moon is a dynamic partner to Earth, a natural archive of cosmic history and a gateway to humanity's future exploration of space. Around 4.5 billion years ago, the solar system was a chaotic and violent place. Planets were still forming from the leftover debris of the Sun's birth, and countless rocky bodies, from small asteroids to Mars-sized protoplanets, roamed the young system in unstable orbits. Earth, still in its infancy, was not the calm, life-filled world we know today. Instead, it was a molten sphere with a thin crust constantly being reshaped by impacts, volcanic activity, and internal heat. In this turbulent era, an event occurred that would change the fate of our planet forever: the birth of the Moon. Among the various hypotheses about how the Moon formed, the giant impact theory remains the most widely accepted. According to this idea, Earth's early days were interrupted by a cataclysmic collision with a Mars-sized body, often referred to as Theia. Theia itself may have been a protoplanet that had developed in a nearby orbit around the Sun, gradually moving closer to Earth due to gravitational interactions. At some point, the trajectories of the two worlds intersected in a cosmic accident that was both destructive and creative. The collision was unimaginably violent. Theia struck Earth at an oblique angle, releasing energy equivalent to billions of nuclear bombs. This was not a gentle merging of two worlds. It was a planetary-scale explosion that vaporized enormous amounts of rock and metal. In the aftermath, both Earth and Theia were partially destroyed, their outer layers blasted into space in a cloud of molten and vaporized debris. The core of Theia likely merged with Earth's own core, contributing to the planet's mass and composition. The material that did not fall back onto Earth formed a vast, glowing disk of rock and gas encircling the battered planet. This debris disk, heated to extreme temperatures, was a temporary and unstable structure. Within days to weeks, gravity began to draw the scattered material together. The heavier particles clumped first, forming small moonlets, while lighter gases and dust followed. Over the course of perhaps a few months, or at most a few years, these fragments merged into a single, dominant body, the Moon. Initially, the Moon orbited much closer to Earth than it does today, perhaps only 20,000 to 30,000 kilometers away, appearing far larger in the sky and raising massive tidal forces on the molten surface of our planet. The giant impact theory explains several key mysteries about the Moon. First, lunar rock samples brought back by the Apollo missions show striking chemical similarities to Earth's mantle, particularly in oxygen isotope ratios. This suggests the Moon was formed from material originating largely from Earth rather than an entirely separate body. Second, The moon is deficient in volatile elements, materials that vaporize easily, indicating it formed in a high-temperature environment, consistent with the aftermath of a massive impact. Third, the moon's relatively small iron core implies that most of the iron from Theia ended up merging with Earth's core, leaving the moon as a lighter, rockier companion. For decades, alternative theories competed with the giant impact hypothesis. The capture theory suggested that the moon formed elsewhere in the solar system and was later captured by Earth's gravity. However, this would require an improbable set of conditions to slow the moon enough for capture without it simply colliding with Earth or escaping back into space. The co-formation theory proposed that the moon and Earth formed together from the same region of the protoplanetary disk, like a double planet. While this might explain their similar compositions, it struggles to account for the moon's lower density and lack of volatiles. The fission theory, an older idea, suggested that the moon spun off from a rapidly rotating young Earth, but the physics of such a process do not match current models. Modern refinements to the giant impact theory have introduced new possibilities. Some simulations suggest that Theia's composition may have been nearly identical to Earth's, explaining why the moon's material seems so Earth-like. Other models explore the idea that the impact might have been so energetic that it vaporized both bodies entirely, forming a shared cloud of material from which Earth and Moon later recondensed, a scenario known as the Sinestra model. This could help resolve lingering questions about isotope ratios and the exact nature of the impact. Regardless of the precise details, the Moon's early days were far from peaceful. The young moon, still glowing with residual heat from its formation, experienced intense volcanic activity as its interior cooled. Its surface was bombarded by leftover debris from the solar system's formation, creating craters that can still be seen today. Tidal interactions between the moon and the molten Earth generated enormous waves of rock and magma, gradually slowing Earth's rotation and causing the moon to drift outward. Within a few tens of millions of years, the moon became tidally locked, showing the same face to Earth, a configuration that has persisted ever since. The moon's birth had profound consequences for Earth's future. The presence of such a large satellite helped stabilize Earth's axial tilt, preventing chaotic swings in climate that could have hindered the development of life. The tidal forces generated by the moon influenced the mixing of ocean waters and may have played a role in the chemical cycles that nurtured early life. Without the moon, Earth's history might have been dramatically different, perhaps less hospitable to the complex biosphere that eventually arose. From a cosmic perspective, the moon's origin is a story of destruction and renewal. The collision that could have obliterated Earth instead gave rise to a unique planetary partnership. The scars of that event are still written in the moon's composition and in the tilt and spin of our planet. Every time we look at the moon, we are seeing the product of an ancient catastrophe that reshaped our world and gave us a steadfast companion for billions of years. As research continues, scientists refine their models with data from lunar missions, advanced simulations, and studies of planetary formation. Each new finding brings us closer to understanding exactly how Theia and Earth came together in that moment. The moon is not simply a passive witness to our planet's history. It is a survivor of the same cosmic forces that shaped Earth, and it carries within it the memory of our shared origin story. In the moments following its violent birth, the moon was a very different world from the quiet, airless sphere we see in our night sky today. It was still hot from the colossal collision that created it, glowing faintly with the heat of molten rock. The newborn moon's proximity to Earth meant that tidal forces between the two bodies were intense, constantly kneading the moon's interior and adding even more heat to its already boiling state. The surface was not yet solid. Instead, it was a roiling ocean of magma. a planetary-scale sea of molten rocks stretching from horizon to horizon. This magma ocean stage was one of the most important periods in the Moon's geological history because it set the foundation for everything that followed. In this molten state, the Moon's interior began to separate into layers, a process known as differentiation. Heavy materials, such as iron and nickel, sank toward the Moon's center to form its small metallic core, while lighter silicates floated upward, eventually cooling to form the crust. The crust began as a thin, fragile skin that gradually thickened as the Moon radiated heat into space. The composition of the lunar crust tells us a great deal about this early stage. One of its main components is anorthosite, a light-colored rock rich in plagioclase feldspar. This mineral floated to the surface during the solidification of the magma ocean, forming the bright highlands that still dominate much of the Moon's visible face today. These highlands are the Moon's oldest surviving terrain, fossilized remnants of the planet's first solid surface. The darker volcanic plains, known as Maria, would not appear until hundreds of millions of years later. The first million years were also marked by an unrelenting bombardment from space. The solar system at that time was filled with leftover debris from planetary formation, asteroids, comets, and planetesimals on unstable orbits. Earth and Moon, locked in their gravitational dance, were prime targets for these stray objects. Every impact added new scars to the Moon's surface, from small pits to massive basins hundreds of kilometers across. Because the Moon lacked an atmosphere, there was no air to burn up incoming meteors, and no weather or geological processes to erase the marks they left. Each crater was preserved almost exactly as it formed, creating a running record of solar system history etched into stone. One of the largest of these early impacts may have been responsible for forming the South Pole, Aitken Basin, a gigantic depression on the Moon's far side over 2,000 kilometers in diameter. If this impact occurred during the Moon's first million years, it would have been a cataclysmic event, excavating material from deep within the crust and possibly altering the Moon's rotation. Other large basins, such as the Imbrium and Serenitatis, may also have had their origins in this early period, though many scientists place them slightly later, during what is called the Late Heavy Bombardment. The relentless impacts did more than just scar the Moon's surface. They also influenced its interior. The largest impacts could penetrate deep enough to momentarily melt parts of the crust or even tap into the molten layers below. This mixing redistributed materials and may have sped up the cooling process in some areas while delaying it in others. Smaller impacts pulverized surface rocks into a fine, dusty soil known as regolith, which even in the Moon's first million years began to blanket its surface. Over billions of years, this regolith would grow thicker, but its origin traces back to this chaotic beginning. While the crust was forming and the impacts continued, the Moon's internal heat was slowly bleeding away into space. The lack of a thick atmosphere or insulating blanket of gases meant that the Moon cooled more quickly than Earth, which retained much more heat in its larger, denser interior. This rapid cooling allowed the crust to stabilize, but also set the Moon on a path toward geological quietness. Volcanic activity, which would later flood some basins with dark basalt, was already becoming limited in scope compared to what we see on larger planets. The Moon's close relationship with Earth during this time played a subtle but critical role in its development. Being so close to its parent planet, only a fraction of its current distance, the Moon experienced enormous tidal forces. These tides did not produce ocean waves, of course, but instead stretched and squeezed the Moon's entire body. This constant flexing generated internal friction and heat, which may have prolonged the magma ocean stage and delayed complete crust solidification in some regions. It also contributed to the Moon's early tidal locking, a process in which the same hemisphere came to face Earth permanently. This would have happened relatively quickly, possibly within just a few million years, locking in the familiar near side and far side we see today. From Earth, the early moon would have been a spectacular sight, hanging far larger in the sky than it does now. Its glowing, molten surface would have been visible to the naked eye, a fiery orb, sometimes veiled in steam-like vapor from rock being vaporized by impacts. Over time, as the crust formed and the glow faded, the first bright highlands and dark scars from massive impacts would have begun to emerge, creating a surface already shaped by cosmic violence. The heavy cratering we see today is largely the result of this early era. Because the moon has no atmosphere, no plate tectonics, and very little erosion, the surface preserves ancient features that on Earth would have long since disappeared. In fact, much of what we know about the early solar system's impact history comes from studying the moon's cratered face. Each crater is like a time capsule, holding clues about the size, speed, and composition of the object that made it. In the moon's first million years, these craters accumulated so quickly that by the end of this period, much of the surface we see today was already in place in its basic form. The contrast between the moon's rugged highlands and smoother basins began to emerge during this time as well. While the highlands represent the original crust formed from the magma ocean, the basins were carved by impacts so massive they reshaped the local landscape. These basins would later become the sites of volcanic flooding, creating the Maria, but in the first million years, they were raw, jagged scars, some still partially molten from the energy of the impacts that made them. By the close of its first million years, the moon had transitioned from a molten, chaotic newborn into a more stable, recognizable world. Its crust had largely solidified, though volcanic and impact processes still shaped its surface. It had become tidally locked to Earth, establishing the fixed near side and far side that would remain for billions of years. And it had accumulated a permanent record of the early solar system's violent environment, preserved in craters, basins, and highland rocks. In this sense, the moon's first million years were both an ending and a beginning. The ending was the final phase of its birth, a cooling from chaos into order, a settling of materials into distinct layers, and the locking of its rotation. The beginning was the start of its long geological story, a tale told in stone, preserved better than almost anywhere else in the solar system. From this point forward, the moon would continue to evolve, but its basic character, the bright highlands, the ancient craters, the absence of an atmosphere, was already set. It was a small, resilient world, forged in fire and shaped by impacts, destined to orbit Earth as both a partner and a witness for the rest of its history. After its fiery birth and turbulent first million years, the moon entered a long, gradual process of change that would define its geological personality for the rest of its existence. The period that followed was one of cooling, reshaping, and quieting down. The moon transformed from a molten, crater-pocked infant into the more stable, though still dynamic, world we know today. This chapter of lunar history is marked by the slow loss of internal heat, the fading of volcanic activity, and the emergence of some of its most distinctive features, the vast, dark plains called Maria and the rugged mountain ranges that ring ancient impact basins. As the moon radiated its heat into space, the magma ocean that had once covered its surface continued to solidify from the top downward. The lighter minerals, like plagioclase feldspar, had already floated to form the highland's crust, but the denser materials, pyroxene, olivine, and other basaltic rocks, remained beneath. Pockets of molten rock persisted in the lunar mantle for hundreds of millions of years, kept warm by residual heat from the moon's formation and by tidal flexing from its close relationship with Earth. This internal heat fueled volcanic activity long after the crust had formed. Early eruptions may have been explosive in nature, venting gases and ejecting molten material over great distances. But over time, the style of volcanism shifted toward calmer, flood-like eruptions of low-viscosity basalt. These massive flows poured across the surface, filling low-lying areas and smoothing over older terrain. The largest of these flooded regions became the Maria, Latin for seas, named by early astronomers who mistook them for bodies of water. The Maria are darker than the highlands because they are composed of basalt, which is denser and less reflective than the anorthosite-rich crust. These plains are concentrated mostly on the near side of the moon, a fact that puzzled scientists for decades. One explanation lies in the thickness of the crust. The far side's crust is significantly thicker, making it harder for magma to break through, while the near side's crust is thinner, allowing more frequent volcanic flooding. This asymmetry may have roots in the moon's earliest tidal locking, when the Earth-facing side remained slightly warmer, delaying complete crust solidification there and leaving it more geologically active for a longer period. The formation of Maria was closely tied to some of the moon's largest impact events. When enormous asteroids struck the moon, they blasted out vast basins, fracturing the crust and exposing the mantle beneath. Over time, magma from the interior welled up through these fractures, slowly flooding the basins. The Imbrium, Serenitatis, and Crisium basins are among the most famous examples. The flooding process wasn't instantaneous. It could take tens or even hundreds of millions of years for volcanic activity to fully fill a basin. The impacts that created these basins also produced towering mountain ranges. When a massive asteroid slammed into the moon, the shock waves rippled through the crust, pushing up rings of mountains around the crater's edge. The Montes Apenninus, Montes Caucasus, and Montes Alpes are striking remnants of this process, forming rugged arcs that still dominate the lunar landscape. These ranges are not tectonic mountains like those on Earth. Instead, they are frozen waves of rock thrown up by unimaginable forces in a single moment of destruction. As the moon's interior cooled further, volcanic activity gradually waned. By about 1 billion years ago, large-scale basalt flooding had ceased entirely, although some evidence suggests that small, localized eruptions may have occurred as recently as 100 million years ago. Without a steady supply of magma, the moon became geologically quiet, entering what is often called its stagnant lid phase. Unlike Earth, whose crust is constantly recycled by plate tectonics, the moon's crust is fixed, preserving ancient features in pristine detail. Cooling also meant that the moon's interior began to shrink slightly. As the mantle contracted, it caused the crust to crack and shift, producing features known as lobate scarps, cliff-like structures that can extend for kilometers. These scarps are relatively young in geological terms, some perhaps less than 50 million years old, showing that the moon's interior is still cooling and adjusting even today. Throughout this slow transformation, the moon continued to be shaped by impacts. While the rate of collisions decreased dramatically after the late heavy bombardment around 3.8 billion years ago, space is never entirely empty, and meteoroids still struck the surface regularly. Smaller impacts peppered both highlands and Maria, creating the pitted, textured appearance we see through telescopes. Because there is no atmosphere to erode these marks, even tiny craters remain for billions of years. The Maria and mountain ranges created during this era became landmarks for early astronomers and remain essential features for modern lunar scientists. The contrast between the bright, ancient highlands and the darker, younger Maria tells a clear story of the moon's evolution. First, the violent creation of basins by impacts, then the slow flooding of those basins by volcanic activity, and finally the long, quiet cooling that left the surface frozen in time. From Earth's surface, these changes would have been noticeable across vast spans of time, though invisible on a human scale. In the deep past, as the Maria filled with basalt, the moon's appearance would have shifted subtly, with dark patches slowly spreading across its face. These would have stood in contrast to the bright highlands, giving the moon the distinctive pattern that has inspired countless myths and legends. The end of major volcanic activity marked the beginning of the moon's geological retirement. With its heat nearly gone and no internal engine to drive change, the moon settled into its role as a largely static world. This geological stillness, while making the moon a dead world in the dynamic sense, also preserved its surface as an unparalleled record of solar system history. Every crater, ridge, and mountain range is a page from a book written over billions of years. The evolution of the moon was not only a matter of internal cooling, but also a reflection of its relationship with Earth. As tidal interactions gradually pushed the moon farther away, the gravitational forces between the two bodies weakened slightly, reducing tidal heating and hastening the moon's transition to geological inactivity. Today, the moon continues to drift away at a rate of about 3.8 centimeters per year, a legacy of the same tidal forces that shaped its early history. In summary, the moon's evolution after its early chaos was a story of slowing down. The magma ocean solidified, volcanic activity peaked and then faded, impact basins filled with basalt to form the Maria, and towering mountain ranges froze in place as monuments to colossal impacts. The surface became a permanent record of ancient events, with little to erase or obscure them. The moon cooled, contracted, and settled into the quiet companion we see today, still moving away from us, still wearing the marks of its violent youth, but no longer reshaping itself from within. This long, slow transformation gave the moon its present face, the one that has inspired humanity's gaze for thousands of generations, and it set the stage for the world that would one day be visited by explorers from its neighboring planet. When the moon first formed, its relationship with Earth was far more intense than it is today. The two worlds were locked in a gravitational embrace, with the moon orbiting much closer, only a fraction of its present distance. From this proximity came powerful effects that would shape Earth's rotation, climate, and even the evolution of life. The early interactions between Earth and its new satellite were not simply a background detail in planetary history. They were fundamental forces that influenced the entire trajectory of our planet's development. One of the most profound contributions of the moon to Earth's stability lies in its effect on our planet's axial tilt. The axis is the imaginary line around which Earth rotates, and it is currently tilted at about 23.5 degrees relative to its orbital plane around the Sun. This tilt is responsible for the changing seasons, as different hemispheres receive more or less sunlight throughout the year. Without the moon, the gravitational tug of the Sun, along with the influence of other planets, especially massive Jupiter, could cause Earth's axial tilt to vary wildly over time. Such chaotic shifts might swing the tilt from nearly upright to severely inclined, producing extreme and unpredictable climate changes. The moon acts as a stabilizing agent. Its gravitational pull creates a torque on Earth's equatorial bulge, resisting large variations in axial tilt. This stabilizing effect has kept Earth's obliquity changes modest, oscillating within a narrow range over tens of thousands of years. These subtle changes, known as Milankovitch cycles, still influence climate patterns, but they are gentle compared to the dramatic swings that might occur without the moon. In essence, the moon has been a guardian of climate stability, helping to maintain conditions favorable for the emergence and persistence of complex life. Another key interaction between the moon and Earth comes from tidal forces. Tides arise because the moon's gravity pulls more strongly on the side of Earth facing it than on the far side, creating a stretching effect. This stretching produces two bulges in Earth's oceans, one on the side facing the moon and another on the opposite side. As Earth rotates, these bulges move across the surface, creating the familiar cycle of rising and falling tides. In the moon's early days, when it was much closer, tidal forces were far stronger. The tidal bulges were higher, and the friction generated by the movement of ocean water against the seafloor was more intense. This tidal friction acted as a brake on Earth's rotation, gradually slowing the length of the day from a mere 6 hours in the moon's infancy to the 24 hours we experience now. The energy lost from Earth's rotation was transferred to the moon, pushing it into a higher orbit. This process continues today, with the moon drifting away at about 3.8 centimeters per year. Tides have been more than just a geophysical curiosity. They may have played a role in the origin and evolution of life itself. In the shallow coastal environments of early Earth, tides would have periodically flooded and exposed areas of land, creating cycles of wetting and drying. These cycles could have concentrated organic molecules and provided natural laboratories for chemical reactions, possibly contributing to the formation of life's first building blocks. Later, as life evolved, tidal rhythms influenced the behavior and reproduction of many species, from marine invertebrates to birds and fish. Even humans, though less directly tied to the tides, have used them for navigation, fishing, and agriculture for millennia. The moon's influence on climate extends beyond stabilizing axial tilt. The tidal mixing of ocean waters, driven in part by lunar gravity, helps regulate Earth's climate system. By mixing surface and deep waters, tides aid in the distribution of heat, nutrients, and dissolved gases across the oceans. This process supports marine ecosystems and affects the global carbon cycle, which in turn influences atmospheric composition and temperature. Without the moon, tidal mixing would be much weaker, potentially leading to more stagnant oceans and less stable climate conditions. In the deep geological past, the combination of a faster spinning Earth and a closer moon created a dramatically different world. Days were shorter, tides were stronger, and the moon loomed large in the sky, several times its current apparent size. Over millions of years, tidal friction continued to slow Earth's rotation and push the moon farther away. As this happened, tidal forces weakened, but their long-term effects had already been imprinted on Earth's environment and life. The moon's gravitational embrace has also influenced the geological evolution of our planet. The constant rise and fall of tides generate stresses in Earth's crust, particularly in shallow seas and along coastlines. In regions where ocean tides interact with geological faults, these stresses can subtly contribute to seismic activity. While tidal triggering of earthquakes is not a primary driver of tectonics, it serves as another example of the subtle but pervasive ways the moon interacts with our world. Culturally and biologically, the moon's influence has been deeply woven into Earth's story. Many organisms evolved to take advantage of lunar cycles, using the predictable waxing and waning of the moon to time reproduction, migration, or feeding. Coral spawning, for example, often coincides with specific lunar phases, ensuring that gametes are released into the water at the same time for maximum fertilization success. For early humans, the moon provided light during the night, influencing hunting, gathering, and travel patterns. Its phases became a natural calendar, guiding agricultural cycles and ceremonial events. The interaction between Earth and the moon has not been a static arrangement. It has evolved over time and continues to change. As the moon moves farther away, its tidal influence will diminish, and Earth's rotation will slow even more. In the far future, billions of years from now, Earth and Moon could become tidally locked to each other, with the same hemisphere of Earth always facing the Moon, just as the Moon always shows one face to us now. This would produce extraordinarily long days and nights, drastically altering the climate and perhaps making the planet less hospitable to life. For now, however, the balance remains favorable. The Moon's gravitational pull continues to stabilize Earth's tilt, drive tides, and subtly shape climate patterns. It is a quiet partnership, one that works in the background, unnoticed by most, yet essential to the world we know. Without the Moon, Earth might have been a far less stable and predictable planet, with erratic seasons, chaotic climate shifts, and perhaps a different evolutionary path for life. In a universe where most planets either lack moons or have satellites too small to exert significant influence, Earth's large and well-placed moon stands out as an exceptional case. Its stabilizing presence has acted like a planetary insurance policy, reducing the risks of extreme environmental swings and supporting the long-term habitability of our world. This interplay of gravity, motion, and time between Earth and Moon is not just a matter of orbital mechanics. It is a story of two worlds whose destinies have been intertwined since a cataclysmic impact billions of years ago. The Moon may be small compared to Earth, but its influence has been disproportionately large. From controlling the rhythm of the tides to keeping Earth's seasons regular, it has been a silent architect of the conditions that made our planet a cradle for life. This ancient partnership, forged in fire and sustained by gravity, remains one of the most remarkable relationships in the solar system. The Moon is not just Earth's companion. It is a co-author of our planet's history, and its quiet pull continues to shape the story of life on Earth. The Moon is not fixed in the sky. Though it may seem constant in its orbit, unchanging night after night, it is in fact slowly slipping away from us. At a rate of roughly 3.8 centimeters per year, about the speed at which fingernails grow, the Moon is drifting farther from Earth. This movement is imperceptible on human timescales, but over millions and billions of years, the effects add up, subtly reshaping the relationship between the two bodies. Understanding why this happens and what it means for the future requires a closer look at the complex interplay of gravity, tides, and orbital mechanics. The mechanism behind the Moon's retreat is rooted in the same tidal forces that create the rise and fall of our oceans. The Moon's gravity pulls on Earth, raising two tidal bulges, one on the side facing the Moon and one on the opposite side. These bulges are not perfectly aligned with the Moon because Earth rotates much faster than the Moon orbits. As a result, the bulge on the side facing the Moon is slightly ahead of the Moon's position in its orbit. This misalignment means that Earth's gravitational pull on the bulge tugs the Moon forward in its orbit. In orbital mechanics, pulling an object forward increases its orbital energy. The Moon responds to this added energy by moving into a higher orbit, farther from Earth. At the same time, the gravitational interaction between the bulge and the Moon exerts a backward pull on Earth's rotation, slowing it down. This exchange of energy between Earth's rotation and the Moon's orbit is a transfer of angular momentum, and it's a process that has been happening since the Moon first formed. In the Moon's early history, when it was much closer to Earth, this tidal braking effect was much stronger. Back then, the day on Earth lasted only a few hours, and the tidal bulges were enormous. The friction generated by these tides transferred angular momentum to the Moon's orbit at a rapid rate, causing it to move outward quickly, perhaps tens of centimeters per year or more. Over time, as the Moon moved farther away, tidal forces weakened, and the rate of recession slowed to what we measure today, around 3.8 centimeters annually. The current measurement comes from a precise scientific method, lunar laser ranging. During the Apollo missions, astronauts placed special retroreflectors on the moon's surface, essentially mirrors designed to reflect laser beams directly back to their source. By firing lasers from Earth and measuring the time it takes for the beam to return, scientists can calculate the exact distance to the moon with centimeter accuracy. Repeating these measurements over decades has confirmed the steady outward drift. The consequences of this slow retreat are subtle now, but will become more dramatic over long stretches of time. As the moon moves away, the strength of its gravitational pull on Earth diminishes, and with it, the size of the tidal bulges. Tides will gradually become weaker, affecting coastal ecosystems that have evolved around their current patterns. Marine life that relies on tidal cycles for reproduction, feeding, or migration may adapt, or in some cases, struggle to survive, if tides weaken significantly. Another long-term consequence is the continued slowing of Earth's rotation. Every time the moon steals a bit of Earth's rotational energy, our days grow ever so slightly longer. Right now, the length of a day increases by only about 1.7 milliseconds per century, an imperceptible change to us, but a significant one over geological timescales. Hundreds of millions of years from now, the day could be hours longer than it is today. This gradual change points toward a distant future in which Earth and Moon become tidally locked to each other. The Moon is already tidally locked to Earth, always showing the same face to us. In the far future, billions of years from now, the same will happen in reverse. Earth's rotation will slow until it matches the Moon's orbital period. When that happens, the same side of Earth will always face the Moon, and the Moon will appear fixed in the sky for anyone on that hemisphere, while it will never be visible from the opposite hemisphere. In such a locked system, the Moon's orbit would stabilize, and its outward drift would stop. However, the Sun's evolution will almost certainly disrupt this scenario before it can fully play out. The Sun will expand into a red giant in about 5 billion years, altering the gravitational balance of the solar system and possibly engulfing Earth entirely. But if we imagine a universe where the Sun remains stable, Earth and Moon would eventually become like Pluto and its moon Charon, two worlds eternally facing each other, locked in gravitational balance. Looking backward in time, the Moon's current recession rate also allows scientists to reconstruct its past. If we extrapolate the rate of drift into the past, we find that the Moon would have been much closer to Earth billions of years ago, dominating the sky and producing enormous tides. However, the rate of recession has not been constant. Geological evidence suggests it has varied depending on the configuration of Earth's oceans and continents. When ocean basins are shaped in ways that amplify tidal effects, more energy is transferred to the Moon's orbit, and it moves away faster. Conversely, when the configuration dampens tidal effects, the recession slows. This interplay between geology and orbital mechanics means the Moon's journey outward has been a complex, uneven process. There are also implications for the stability of Earth's climate. The Moon's distance affects the strength of its stabilizing effect on Earth's axial tilt. As it moves farther away, its grip on our tilt weakens slightly. In the distant future, Earth's axial tilt could become more susceptible to gravitational influences from other planets, potentially leading to greater variation in climate over long timescales. Though the change would be gradual, it could have significant consequences for habitability if it coincided with other major shifts in Earth's environment. For now, the Moon's retreat is a slow, steady process that has minimal impact on our daily lives. Yet it is a reminder that the Earth-Moon system is not static. It is an evolving partnership shaped by the laws of physics. Every high tide we see is part of this ongoing exchange of energy. Every fraction of a millisecond added to our day is part of a process that began billions of years ago and will continue long after humanity is gone. The image of the moon drifting away might seem melancholy, our closest celestial companion slowly leaving us. But it is also a story of balance and connection. The very force that pushes the moon away is the same one that binds it to us. Gravity, combined with motion, creates this dynamic relationship. Earth spins, tides rise and fall. The moon gains energy and drifts outward. It is a cosmic dance that began with a violent impact and has since unfolded in slow motion, shaping the history of both worlds. In the end, the moon's ongoing drift is part of the grand story of the solar system, where nothing remains fixed forever. Planets migrate, moons shift, and orbits evolve over time. The moon's retreat from Earth is a gentle reminder of the constant change that underlies even the most seemingly eternal sights in the sky. Each centimeter it gains each year is another step in a journey it has been on for 4.5 billion years. A journey that continues, quietly and steadily, beneath the familiar glow of our nearest neighbor in space. Long before humans understood the moon as a celestial body orbiting Earth, they lived by its rhythms. For early societies, the moon was not simply a light in the night sky. It was a timekeeper, a compass, a symbol woven into stories, and a force that shaped daily life. In an age without clocks, compasses, or written records, the moon's steady cycles provided a rare kind of reliability in a changing world. It was both a practical tool and a canvas for the imagination, influencing everything from agriculture to religion. One of the earliest ways humans used the moon was as a natural calendar. The moon's phases repeat in a cycle of about 29.5 days, from new moon to full moon and back again. This pattern is easily observed with the naked eye, even without any scientific instruments, and it repeats with remarkable consistency. Early people could count nights from one full moon to the next to measure months, track seasons, and organize activities like planting, harvesting, hunting, and gathering. The predictability of the lunar cycle gave humans their first method of keeping time beyond the daily rise and set of the sun. In many ancient cultures, these lunar months formed the backbone of the earliest calendars. Archaeological evidence, such as notched bones from the Upper Paleolithic era, suggests that humans may have been tracking the moon's phases for more than 25,000 years. The Ishango bone, discovered in Africa, is one such artifact, with carved marks that may represent a lunar calendar. Over time, societies developed more sophisticated lunar-based systems, adjusting them to align with the solar year, so they could track seasonal changes as well. The moon also played a vital role in navigation. For early travelers, whether moving across deserts, forests, or open seas, the moon was a guiding light. Its predictable path across the sky made it a reference point for direction. Mariners learned to use the moon alongside the stars to find their way at night. Because the moon's position relative to the stars changes in a regular way, it could even help estimate longitude when combined with careful timekeeping, a skill mastered much later by advanced civilizations. Before the invention of the magnetic compass, such celestial navigation was the primary means of orienting oneself during long journeys. Beyond its practical uses, the moon quickly became a powerful symbol in human culture. Its changing phases made it seem alive, as though it waxed and waned with purpose. Early myths often personified the moon as a god, goddess, or spirit, attributing to it control over life, death, fertility, and time. In many traditions, the moon was linked to femininity because of its monthly cycle's similarity to the human menstrual cycle, reinforcing associations with fertility, childbirth, and renewal. For example, in ancient Mesopotamia, the moon god Sin, also called Nana, was a central figure, associated with wisdom and the passage of time. In ancient Egypt, the moon was connected to Thoth, the god of knowledge, writing, and measurement, who helped keep the cosmos in balance. In China, the moon goddess Chang'e became the focus of stories about immortality and love, and the Mid-Autumn Festival, celebrated for thousands of years, honors her and the moon's harvest time fullness. Among many indigenous cultures in North America, the moon was seen as a guide, a protector, or a timekeeper, with months named after natural events that occurred under its light, like the strawberry moon or snow moon. These myths were not just entertainment. They were a way of encoding practical knowledge into stories that could be passed down through generations. Myths might explain when a plant crops, when animals would migrate, or when the tides would be highest, all tied to the moon's phases. This blending of observation and storytelling created a shared cultural memory, binding communities together around a common understanding of the natural world. The moon's influence on tides also fed into its mystical reputation. Coastal communities could not help but notice the connection between the moon's phases and the changing sea. The regular rise and fall of tides, so critical for fishing, shellfish gathering, and trade, seemed to follow the moon's lead. Without the benefit of modern science, it was natural for people to see the moon as a ruler of the waters and a force that could shape human fortune. Art, too, was shaped by the moon. Prehistoric cave paintings sometimes depict the crescent shape, and in later eras, lunar imagery appeared on pottery, jewelry, and temple carvings. The moon's light transformed the landscape at night, turning deserts silver, making snow sparkle, or casting long shadows through forests. Poets, musicians, and storytellers drew inspiration from its beauty and its mystery, weaving it into love songs, epics, and sacred rituals. Lunar observation was also tied to early science. Ancient astronomers recorded the moon's movements, mapped its path through the constellations, and tracked eclipses. In doing so, they laid the groundwork for predicting celestial events. In Babylonia, astronomers could forecast lunar eclipses centuries before modern instruments existed. In Mesoamerica, the Maya created complex lunar tables that helped them plan agricultural and ceremonial activities. The moon became both a clock and a laboratory for studying the heavens. The moon's phases often structured human life in direct, tangible ways. Some societies held markets, festivals, or religious ceremonies on specific lunar dates. Others used the full moon for night work, hunting, or travel, taking advantage of the extra light. In agricultural communities, planting or harvesting might be timed to the waxing or waning moon, based on the belief, sometimes supported by observation, that crops behave differently depending on the moon's phase. In the Paleolithic and Neolithic eras, when survival depended on careful observation of the environment, the moon's regular cycle was a rare constant in an unpredictable world. Seasons could vary, animals might migrate early or late, and weather could be harsh, but the moon's phases never failed to return. This constancy may have been one reason it became such a central figure in myth and ritual. It was a dependable companion in a universe that often seemed chaotic. The moon also shaped human sleep and behavior. Before artificial lighting, moonlight determined how active people could be at night. Full moons allowed for extended evening gatherings, travel, or hunting. Folklore about the madness of the full moon, while scientifically questionable, reflects the recognition that brighter nights change human and animal activity. Even predators and prey adjusted their habits around the moon's light, influencing the rhythms of life in subtle ways. As civilizations grew, the moon retained its importance even in the presence of the sun's dominance in many calendars. Lunar solar systems emerged, blending the moon's months with the sun's year to create more accurate measures of time. Festivals like Ramadan in Islam, Easter in Christianity, and the Lunar New Year in many East Asian cultures still reflect the moon's role in marking sacred and cultural occasions. In short, The moon in early human life was far more than a passive background object. It was an essential part of survival, a guide in the darkness, a calendar in the sky, a shaper of tides, and a source of wonder. Its phases dictated the rhythm of life. Its presence guided travelers across unknown lands and seas, and its cycles wove themselves into the spiritual and cultural fabric of countless societies. The moon was, in a real sense, humanity's first companion in exploring the mysteries of the cosmos, visible to everyone, shared by all, and deeply embedded in our earliest attempts to understand the world. The legacy of that early relationship still echoes today. Even in an age of atomic clocks and GPS satellites, the moon remains a symbol of time, navigation, and mystery. We may no longer depend on it for our daily survival, but its steady presence in the sky is a reminder of the deep and ancient connection between human life and the rhythms of the natural world. That bond began when the first people looked up at the night sky and noticed the moon's changing face, a simple observation that shaped the very foundations of human culture. From the moment humans began telling stories, the moon was there, looming over their imaginations like a silver lantern in the night. Its shifting shape, glowing presence, and mysterious influence over the tides and night creatures made it an irresistible subject for myth. Across time and continents, the moon became a goddess, a god, a monster, a mirror to the human soul, a place of magic and prophecy, and a harbinger of change. These myths, while vastly different in detail, share a common fascination with the moon as something alive, something more than a distant rock in the sky. In many cultures, the moon is personified as a goddess. The cyclical waxing and waning mirrored the cycles of fertility, menstruation, and renewal, leading to a strong association with femininity and the life-giving powers of nature. In ancient Greece, the moon was Selene, a radiant goddess who drove her silver chariot across the night sky. Later, Artemis, the virgin huntress, also took on lunar attributes, symbolizing purity, wildness, and protection. In Rome, she became Luna, worshipped in rituals to secure safe childbirth, successful harvests, and protection from evil spirits. These goddesses often represented a balance between nurturing and untamed forces, calm light and darkness, yet commanding respect through their power. In other traditions, the moon was not female but male. In ancient Mesopotamia, the moon god Sin, or Nana, was a wise and serene figure, associated with timekeeping and the cycles of life. The Inuit of the Arctic told stories of the moon as a male figure named Aningan, who chased his sister, the sun, across the sky. In Japanese folklore, the moon deity Tsukuyomi was male, embodying calmness, order, and a sense of distance from earthly affairs. The gendering of the moon varied depending on cultural worldview and the symbolic roles assigned to light and darkness. Many myths explain the moon's phases through tales of pursuit, injury, or transformation. In some Pacific Island traditions, the moon's waxing and waning are the result of it being gradually devoured and then reborn. In the Maori stories of New Zealand, the moon is a woman named Rona, who was snatched into the sky after cursing it during a dark night when she tripped over a tree root. The changes in the moon's shape were seen as her carrying a water gourd, which waxed and waned with the lunar phases. Such stories often personalize the moon, making its distant changes part of an ongoing drama familiar to human life. In Chinese mythology, one of the most enduring lunar legends is that of Chang'e, the moon goddess who drank an elixir of immortality and floated away from Earth to live forever on the moon. She is often depicted with her companion, the jade rabbit, who endlessly pounds herbs in a mortar. This story has been celebrated for centuries during the Mid-Autumn Festival, when people gather to eat mooncakes and admire the full moon, offering food and incense in her honor. Elsewhere, the moon was seen as a place of banishment or refuge. In Hindu mythology, the moon is personified as Chandra, a god who travels across the sky in a chariot. Chandra is also associated with time, night, and the nourishing power of plants. Some Hindu stories tell of gods and heroes cursed to dwell on the moon for a time, reflecting the idea that the moon was a distant yet reachable realm. Not all lunar myths are gentle or romantic. In some cultures, the moon was feared as a devourer or an omen of death. In Central and South America, certain indigenous groups believe that a blood-red moon during an eclipse was caused by a jaguar attacking it, and loud noises or rituals were performed to scare the beast away. Similarly, in parts of Africa, people would drum or shout during an eclipse to protect the moon from harm. These stories often treated lunar events as battles between cosmic beings, with human participation seen as necessary for restoring balance. The moon also appears in myths as a trickster or shapeshifter. Among some Native American tribes, the moon could take human form and wander the earth, testing people's hospitality or punishing wrongdoing. The Kwakwaka'wakw people of the Pacific Northwest tell of a great lunar being who brought light to the dark world by stealing it from another powerful spirit. Such tales connected the moon to themes of cleverness, survival, and the thin line between the sacred and the mischievous. Lunar omens played a large role in many societies. A bright, clear full moon might be seen as a sign of prosperity or a good harvest, while a hazy or oddly colored moon could warn of illness, war, or disaster. Eclipses were especially significant, often interpreted as signs from the gods. The ancient Chinese viewed solar and lunar eclipses as disruptions in the cosmic order, sometimes caused by celestial dragons trying to swallow the sun or moon. The Babylonian astronomers, more scientific in approach, recorded eclipses meticulously, using them to forecast political or military events, though still couched in the language of divine warning. Magic and the moon were inseparable in many traditions. In European folklore, the full moon was believed to be a time when magical powers were at their peak, when spells, love charms, and prophecies were most effective. The moon's light was thought to protect against evil spirits or to awaken supernatural creatures. Most famously, the werewolf, whose transformation was tied to moonlight in later medieval and modern legends. In witchcraft traditions, the waxing moon was associated with growth and attraction, the waning moon with banishment and release, and the full moon with culmination and manifestation. The moon's connection to dreams and madness also left its mark on language. The term lunatic comes from the Latin lunaticus, meaning moonstruck, reflecting the ancient belief that the moon could influence the mind. Bright moonlight, especially in pre-electric eras, could disturb sleep patterns, and this disruption was linked in popular imagination to strange behavior, heightened emotion, or visions. Even in cultures with highly advanced astronomy, the moon retained its mythic qualities. The ancient Maya, who calculated the moon's cycles with extraordinary precision, saw it as the domain of a powerful goddess linked to fertility, weaving, and childbirth. She was both nurturing and dangerous, associated with floods, storms, and the unpredictable forces of nature. For them, scientific observation and spiritual interpretation existed side by side, each reinforcing the other. The universality of lunar myths speaks to the moon's unique place in human experience. Unlike the distant stars or the sun, which is too bright to observe in detail, the moon invites close attention. Its features are visible to the naked eye, and its phases unfold slowly enough for even casual observers to notice patterns. It is both near and far, changing and constant, an eternal presence that nonetheless feels alive. Over centuries, as scientific understanding grew, the moon's myths did not vanish. they transformed. The moon that once housed gods and monsters became the moon of poets, lovers, and dreamers. Its silver light still inspires metaphors for beauty, loneliness, or longing. The cultural images of the moon are a living tradition, evolving alongside humanity's relationship with the night sky. Even today, echoes of these ancient stories can be found in festivals, art, and popular culture. From Chang'e in Chinese space exploration missions to the romantic man in the moon images on greeting cards, the moon's mythical heritage continues to shine through. It reminds us that before we set foot on its surface, we walked its landscapes in our minds, imagining palaces, forests, rabbits, gods, and battles in the shifting light of a timeless, watchful companion. Long before humanity invented writing or built cities, people were already looking to the moon as both a mystery and a measure of time. Its changing shape offered a natural clock in the sky, a cycle that could be counted, predicted, and linked to the rhythms of life. In a world without mechanical instruments, naked eye observation of the moon was one of the most accessible forms of astronomy. Hunters, farmers, sailors, and priests alike learned to recognize the new moon, the first crescent, the waxing half, the full, and the waning phases. This awareness shaped rituals, determined planting and harvesting times, and even helped coordinate social gatherings or migrations. The earliest forms of astronomical record-keeping likely began with lunar observations. Archaeological evidence, such as notched bones and carved stones dating back tens of thousands of years, suggests that prehistoric people marked the number of days between phases of the moon. These early lunar calendars were not abstract scientific tools. They were directly tied to survival, guiding food collection, navigation, and seasonal expectations. As civilizations arose, the moon's role in astronomy deepened. Ancient Babylonians meticulously recorded lunar cycles, recognizing the 29.5-day synodic month and predicting eclipses with impressive accuracy. They developed mathematical methods to track the moon's motion against the background of stars, which allowed them to create reliable calendars and link celestial events to political or agricultural planning. To them, astronomy and astrology were inseparable. The moon was both a celestial body and a bearer of omens. In ancient Egypt, the lunar cycle worked alongside the solar calendar to structure religious festivals. Egyptian priests observed the moon's position and phase to time rituals to the gods, particularly Thoth, who was associated with wisdom, writing, and the measurement of time. The moon's predictable phases also made it a key marker for organizing the ceremonial year. In ancient China, careful naked eye observations of the moon date back more than 3,000 years. Chinese astronomers recorded the moon's phases, tracked its path across the ecliptic, and noted unusual events such as eclipses or halos. They recognized that the moon's position could be used to determine the time of night and even direction for navigation. In the Chinese tradition, lunar and solar calendars were blended into a sophisticated lunisolar system that still influences festivals today. The ancient Greeks brought new ideas to lunar observation, asking not only when the moon would appear in certain phases, but why it changed shape. Philosophers such as Anaxagoras in the 5th century BCE proposed that the moon was a rocky body lit by the sun, not a glowing divine object. This was a radical thought at the time, and it laid the foundation for a scientific understanding of the moon's nature. Later, Aristotle noted that the moon always shows the same face to Earth, which hinted at tidal locking, even if the mechanism was not yet understood. By the Hellenistic period, astronomers like Hipparchus and Ptolemy were measuring the moon's apparent size, tracking its varying speed across the sky, and estimating its distance. While their methods lacked modern precision, they demonstrated that the moon could be studied quantitatively, not just admired or mythologized. Ptolemy's Almagest included detailed models of the moon's motion, which would influence astronomy for over 1,000 years. For most of human history, the moon remained a feature seen only with the naked eye. Observers could make out its phases, its path among the stars, and its role in eclipses, but surface details were limited to vague impressions of light and dark patches. These markings inspired the idea of the man in the moon and other cultural interpretations, but their true nature, whether seas, continents, or shadows, remained speculative. The transformation came in the early 17th century with the invention of the telescope. While not originally designed for astronomy, the telescope quickly became the most revolutionary tool in the study of the moon. In 1609, Galileo Galilei turned a telescope of his own construction toward the moon and saw something that defied centuries of assumptions. The lunar surface was not a perfect, smooth sphere, but a rugged world of mountains, craters, and valleys. Galileo's drawings of the moon, published in his Sidereus Nuncius in 1610, showed detailed shading and the sharp contrast between illuminated and shadowed regions. He noted how the changing angle of sunlight revealed the relief of the terrain, just as it does on Earth. This directly challenged the Aristotelian belief that heavenly bodies were made of an unchanging, flawless substance. If the moon had mountains and valleys like Earth, then it was not fundamentally different from our planet. It was a place, not merely a light in the sky. Galileo was not the only astronomer to examine the moon through a telescope at this time. Thomas Harriot in England and Johannes Hevelius in Poland produced their own lunar maps, improving accuracy and detail. Hevelius's Selenographia, 1647, was one of the first comprehensive atlases of the moon, naming its features and attempting systematic study. Although many of these early names have since been replaced by modern nomenclature, the effort marked a turning point. The moon was no longer just a moving light, but a charted and measurable world. As telescopes improved, so did lunar science. By the late 17th and 18th centuries, astronomers began to suspect that the moon's craters were the result of impacts or volcanic activity. The moon's phases and position were used to refine navigation at sea, especially through the lunar distance method for determining longitude. This practical application of lunar observation made astronomy not just an intellectual pursuit, but a crucial tool for global exploration and trade. Even in this period of scientific advancement, the moon continued to inspire wonder and speculation. Questions arose about whether it might have an atmosphere, water, or even life. These debates would continue until the space age finally settled them. The moon also remained central to calendar making and cultural life, with its cycles still marking religious festivals in many traditions. By the dawn of the 19th century, lunar observation had moved far beyond the myths and omens of antiquity, yet the emotional and poetic connection to the moon remained intact. The merging of careful measurement with imaginative engagement created a unique place for the moon in the birth of astronomy. It served as both the first target for serious astronomical study and the bridge between the ancient skywatchers who tracked its phases and the modern scientists who would one day walk on its surface. The story of the moon in the history of astronomy is, in many ways, the story of humanity's awakening to the possibility that other worlds exist. Once we saw the moon not as a flawless heavenly lantern, but as a real, solid place, the door to the cosmos opened wider. The leap from myth to measurement began with our oldest companion in the sky, and from that first look through a telescope, the moon has never stopped drawing our gaze, both as a subject of scientific inquiry and as a timeless muse. In the middle of the 20th century, the moon became more than just a distant object of study. It became a geopolitical prize. The Cold War rivalry between the United States and the Soviet Union turned space into a new arena for competition, and the moon stood, as the most visible and symbolic target. The space race, as it came to be called, was about more than technology or exploration. It was a contest of ideology, prestige, and national pride. Each side sought to demonstrate its scientific superiority and industrial might, and each milestone in lunar exploration was celebrated as proof of political and technological dominance. The first phase of this contest was marked by robotic, unmanned missions. In 1959, the Soviet Union achieved the first major lunar breakthrough with Luna 1. Originally intended to crash into the moon, the probe instead missed its target and became the first human-made object to enter a heliocentric orbit. While not a direct hit, it proved that the Soviet engineers could send a spacecraft far beyond Earth, a remarkable achievement for the time. Later that same year, Luna 2 succeeded where its predecessor had failed, impacting the moon on September 14, 1959, and scattering small metal spheres engraved with the Soviet emblem across the surface. It was the first human artifact to touch the moon, a feat that resonated deeply in the propaganda war between East and West. But the Soviets were not done. Only a month later, on October 7, 1959, Luna 3 performed one of the most extraordinary missions in the history of space exploration. It photographed the far side of the moon for the first time. Until that moment, humanity had never seen the hemisphere that always faces away from Earth, hidden by tidal locking for billions of years. The grainy, black and white images revealed a strikingly different landscape from the familiar near side. Far fewer dark maria and many more craters. While the pictures lacked sharp detail, they were a revelation, showing that the moon's two faces were geologically distinct. For the United States, these Soviet successes were a wake-up call. The early American lunar program, managed by NASA and the Jet Propulsion Laboratory, faced multiple failures in the late 1950s and early 1960s. The Pioneer and Ranger programs suffered repeated launch failures, communication losses, and crashes. Each Soviet triumph intensified political pressure in Washington, and American engineers worked relentlessly to catch up. Finally, in 1964, Ranger 7 delivered the first close-up images of the moon from an American spacecraft. Unlike the Soviet flybys, Ranger's mission was to deliberately crash into the moon while transmitting high-resolution photos in its final moments. The resulting images, far clearer than anything seen before, revealed surface details down to half a meter in size and provided essential data for future landings. While the Ranger series established a foundation of knowledge, the next step was to achieve soft landings, touching down gently without destroying the spacecraft. The Soviet Luna 9 accomplished this first in February 1966. It used airbags to cushion its landing in Oceanus Procellarum and transmitted panoramic photographs from the surface, showing a rocky plain stretching into the distance. These images debunked fears that the moon's surface might be covered in deep dust that would swallow landers whole, a genuine concern among scientists at the time. The Americans responded swiftly with the Surveyor program, beginning with Surveyor 1 in June 1966. It successfully landed in the Mare Cognitum, returning thousands of photographs and data on soil mechanics, bearing strength, and composition. Over the next 2 years, the Surveyor landers tested lunar surface conditions, practicing maneuvers, and providing vital engineering information for the Apollo missions. While soft landers were proving the feasibility of operating on the moon's surface, both nations also sent orbiters to map and photograph potential landing sites. The Soviet Luna 10, launched in April 1966, became the first artificial satellite of the moon, measuring its gravitational field and studying radiation levels. The U.S. Lunar Orbiter program followed, producing detailed photographic maps of both the near and far sides between 1966 and 1967. These orbital surveys identified flat, hazard-free zones suitable for crewed landings, particularly in the equatorial regions. This period also saw advances in understanding the Moon's environment. Instruments on both Soviet and American probes measured the solar wind, magnetic fields, and micrometeorite flux. It became clear that the Moon lacked a global magnetic field and had only an extremely tenuous atmosphere, conditions that would pose challenges for human explorers. These early missions also confirmed that lunar surface temperatures varied drastically, from searing heat in sunlight to deep cold in darkness, underscoring the need for robust spacecraft design. Each success built momentum toward the ultimate goal, sending humans to the Moon. For the Soviets, this meant developing the massive N-1 rocket and the L-3 lunar landing complex, while for the Americans it meant the Saturn V and the Apollo program. But before humans could fly, automated missions continued to blaze the trail. In April 1967, the Soviet Luna 13 landed and sent back more panoramic images and soil analysis data. In 1968, Luna 14 orbited the Moon to study its gravitational anomalies, later known as mascons, which would influence spacecraft trajectories and landings. These dense regions beneath the lunar maria were likely caused by ancient asteroid impacts and magma flows. Understanding them was crucial for accurate navigation and safe landings. By the late 1960s, the space race was reaching its climax. The United States, learning from Ranger, Surveyor, and Lunar Orbiter missions, had developed a detailed knowledge of the Moon's surface and environmental hazards. The Soviet Union maintained its lead in some areas, such as robotic sample returns. In September 1970, after the peak of the crewed Apollo program, Luna 16 returned 101 grams of lunar soil to Earth, marking the first automated sample return mission. But before that, the first images of the Moon's far side from Luna 3 had already changed the way scientists thought about lunar geology. The far side's thicker crust and fewer maria suggested that the near side's basalt plains were the result of unique heating and volcanic activity, possibly linked to tidal interactions with Earth. These differences became a key focus of later lunar science, influencing landing site selection for both robotic and crewed exploration. Between 1959 and the early 1970s, the Moon went from being a remote and mysterious body to one of the most studied objects in the solar system. Robotic probes mapped its surface, measured its environment, and prepared the way for humanity's greatest leap in space exploration. These missions not only advanced science, but also became symbols of national achievement, each side claiming victories in the name of progress and prestige. The first lunar missions proved that the Moon was accessible and that machines could survive and operate there. They revealed its landscapes in unprecedented detail, exposed its challenges, and inspired the belief that humans could follow. When Neil Armstrong stepped onto the lunar surface in 1969, he did so on the shoulders of these early robotic pioneers. Without Luna 3's first glimpse of the hidden hemisphere, Luna 9's soft landing, Ranger's close-up images, and Surveyor's surface tests, the Apollo program might never have succeeded. The space race began with rockets and rivalries, but it left a legacy of exploration that belongs to all humanity, a shared first chapter in the story of visiting another world. By the end of the 1960s, the Moon had transformed from a distant dream into a reachable destination. Years of intense political competition, rapid technological development, and careful scientific preparation had set the stage for humanity's first steps on another world. The United States, propelled by the urgency of the Cold War and President John F. Kennedy's 1961 challenge to land a man on the Moon before the decade's end, poured unprecedented resources into the Apollo program. The effort brought together more than 400,000 engineers, scientists, technicians, and support staff across NASA, private industry, and academia. The goal was simple in words but monumental in execution. Send astronauts to the moon, land them safely, let them explore, and bring them home. The Apollo program built upon the lessons of earlier missions. Mercury had proven humans could survive in space. Gemini had tested rendezvous, docking, and extended missions. Apollo would integrate all of that knowledge into a single, highly complex sequence of events involving a three-part spacecraft. The Command Module, CM, for crew operations, the Service Module, SM, for propulsion and life support, and the Lunar Module, LM, for landing and ascent from the Moon's surface. The Saturn V rocket, the most powerful launch vehicle ever built, would send it all on a trajectory to the Moon. Before the historic landing attempt, NASA executed a series of missions to test each critical phase. Apollo 7, 1968, proved the command and service modules in Earth orbit. Apollo 8, in December 1968, became the first crewed spacecraft to orbit the Moon, providing stunning photographs of the lunar surface and the now iconic Earthrise image. Apollo 9 tested the lunar module in Earth orbit, while Apollo 10 performed a full dress rehearsal in lunar orbit, descending to within 15 kilometers of the surface before returning to the command module. These flights verified that the systems worked as intended and that the crews were ready for the final challenge. On July 16, 1969, Apollo 11 launched from Kennedy Space Center with Commander Neil Armstrong, Lunar Module pilot Edwin, Buzz, Aldrin, and Command Module pilot Michael Collins. The Saturn V roared to life, lifting its massive payload into Earth orbit before sending it on a 3-day journey to the Moon. After entering lunar orbit, Armstrong and Aldrin boarded the lunar module, named Eagle, and began their descent to the Sea of Tranquility. As they approached, Armstrong realized their automated guidance system was taking them toward a boulder-strewn crater. Taking manual control, he navigated to a safer spot, landing with less than 30 seconds of fuel remaining. Houston, Tranquility Base here. The Eagle has landed. Those words, spoken by Armstrong, announced to the world that humanity had arrived. After hours of preparation inside the lunar module, Armstrong descended the ladder and, at 2:56 Universal Time coordinated on July 21, 1969, stepped onto the lunar surface. His words, "That's one small step for a man, one giant leap for mankind," were broadcast live to an audience of hundreds of millions. Moments later, Aldrin joined him, describing the lunar landscape as magnificent desolation. For over 2 hours, Armstrong and Aldrin explored their surroundings, setting up experiments and collecting samples. They deployed the passive seismic experiment to detect moonquakes, the laser-ranging retroreflector to measure the Earth, moon distance precisely, and the solar wind composition experiment. They also gathered 21.5 kilograms of lunar rocks, soil, and core samples, carefully documenting each one for analysis back on Earth. Meanwhile, Collins remained alone in lunar orbit aboard the Command Module Columbia, maintaining constant readiness to retrieve his crewmates. The Apollo 11 landing was not the end, but the beginning of an extraordinary period of exploration. Apollo 12, in November 1969, demonstrated pinpoint landing capability, touching down near the unmanned Surveyor 3 probe and retrieving parts of it for study. The crew conducted extensive geological investigations, expanding the scientific return of the program. Apollo 13, launched in April 1970, famously suffered an oxygen tank explosion en route to the Moon, forcing the crew to abort the landing and use the lunar module as a lifeboat. The mission's safe return was a triumph of problem-solving under pressure and highlighted the inherent risks of lunar travel. After modifications to enhance safety, Apollo 14 succeeded in landing at the From Morrow Highlands in February 1971, bringing back 42 kilograms of samples and conducting surface experiments. Apollo 15, launched in July 1971, marked a new era of mobility on the Moon. It introduced the Lunar Roving Vehicle, LRV, a battery-powered car that allowed astronauts to travel kilometers away from the landing site, greatly increasing the range of exploration. Astronauts David Scott and James Irwin spent over 18 hours on the surface, collecting more than 77 kilograms of material, including the famous Genesis rock, thought to be a piece of the Moon's original crust. Apollo 16, in April 1972, explored the lunar highlands, providing critical insights into the Moon's geological diversity. The astronauts drove their rover over rugged terrain, performing experiments and gathering more than 94 kilograms of samples. Apollo 17, in December 1972, was the final Apollo mission to the Moon and the only one to include a professional scientist, geologist Harrison Schmitt. Alongside Commander Eugene Cernan, Schmitt spent over 22 hours outside the lunar module, conducting experiments and driving nearly 36 kilometers in the rover. The mission returned 110 kilograms of samples, the most of any Apollo landing. Cernan's final words before departing the Moon expressed hope that humanity would return with peace and hope for all mankind. In total, the Apollo program brought back 382 kilograms of lunar material from 6 successful landings. These samples revolutionized our understanding of the Moon's history and composition. They revealed that the Moon's surface rocks were primarily basalt from ancient lava flows, that its highlands were composed largely of anorthosite, and that its volcanic activity had ended billions of years ago. Analysis of the samples confirmed the giant impact theory's predictions, showing strong similarities in isotopic composition between Earth and Moon. The human landings also left behind a lasting legacy on the Moon's surface. Scientific instruments continued to transmit data for years after the missions ended. The retroreflectors from Apollo 11, 14, and 15 are still in use today, allowing scientists to measure the Moon's drift away from Earth with centimeter precision. Footprints, rover tracks, and the lower stages of the lunar modules remain untouched in the airless environment, preserved as silent monuments to human exploration. The Apollo landings represented a peak of human achievement, combining courage, ingenuity, and international attention in a way rarely matched in history. Yet the program was also a product of its time. The enormous costs, the shifting political climate, and the sense of mission accomplished after Apollo 11 led to the program's premature end. Plans for further landings and even permanent lunar bases were shelved, and for decades afterward, humans would not venture beyond low Earth orbit. Nevertheless, the human landings on the Moon transformed our relationship with space. They demonstrated that exploration on an interplanetary scale was possible with existing technology and careful planning. They expanded human scientific knowledge in ways no robotic mission alone could have achieved at the time. And perhaps most importantly, they inspired generations around the world to imagine futures in which humans could live and work beyond Earth. When the Apollo astronauts looked back at our planet from the Moon, they saw a fragile blue sphere hanging in the darkness, small, precious, and without borders. The photographs and the perspective they brought home became central to the environmental movement and to a broader understanding of humanity's place in the cosmos. The footprints on the Moon are more than physical marks on another world. They are symbols of what can be accomplished when vision, determination, and cooperation come together on a planetary scale. After the final Apollo mission in December 1972, human footsteps no longer disturbed the Moon's silent surface, but exploration did not stop. In the decades that followed, the torch of lunar research passed largely to robotic missions and orbiting satellites. Freed from the cost and risk of crewed flights, space agencies could focus on gathering long-term, high-resolution data, exploring regions unreachable by Apollo, and answering questions that the early landings had left unresolved. This modern era of lunar research has been characterized by international cooperation, improved technology, and a renewed focus on resources, especially minerals and water, that could one day support human life beyond Earth. The immediate years after Apollo saw a lull in lunar activity, especially from the United States, which shifted priorities to the Space Shuttle program and low Earth orbit operations. However, the Soviet Union maintained a presence on the Moon through its Lunar program. Luna 16, 20, and 24 successfully returned small amounts of lunar soil to Earth in the 1970s, while Luna 17 and 21 delivered the Lunokhod robotic rovers. These remotely operated vehicles roamed for kilometers, beaming back images and conducting soil analyses. Though primitive by modern standards, they were technological marvels for their time and proved the feasibility of surface mobility. By the 1990s, the Moon was once again in the sights of multiple nations. A new wave of missions began with the Japanese spacecraft He-10 in 1990, which demonstrated novel navigation techniques. In 1994, the U.S. Department of Defense and NASA jointly launched the Clementine mission, designed initially to test sensors for missile defense, but repurposed to conduct a global lunar survey. Clementine mapped the Moon in multiple wavelengths, revealing mineral distributions and, importantly, providing early evidence of possible water ice in permanently shadowed craters at the poles. This tantalizing discovery shifted scientific priorities, as water on the Moon could be a game-changer for future exploration, serving as drinking water, breathable oxygen, and even rocket fuel when split into hydrogen and oxygen. In 1998, NASA launched Lunar Prospector, a dedicated lunar orbiter equipped with instruments to map the Moon's composition, measure its gravitational field, and search for magnetic anomalies. One of its most significant findings was the confirmation of hydrogen-rich regions at the poles, supporting the hypothesis of water ice deposits. The mission concluded in 1999 with a deliberate crash into a polar crater in hopes of ejecting water vapor for detection, though no definitive signal was observed. The 21st century brought an explosion of activity as more nations entered the lunar arena. ESA's SMART 1, launched in 2003, tested solar electric propulsion while carrying a suite of scientific instruments for high-resolution imaging and spectroscopy. Its mission demonstrated the efficiency of ion engines for interplanetary travel and provided valuable data on the Moon's geology. In 2007, Japan's Kagaya, Selene, orbiter began an ambitious mission to map the Moon in unprecedented detail. With two small relay satellites in supporting orbits, Kagaya studied the Moon's gravitational field, mineral composition, and topography, producing breathtaking high-definition videos of the Earth rising and setting over the lunar horizon. That same year, China joined the race with Chang'e 1, the first step in an ambitious lunar program that would later include orbiters, landers, rovers, and sample return missions. India launched Chandrayaan-1 in 2008, which used a suite of international instruments to map the Moon's surface and confirm the widespread presence of hydroxyl molecules and water ice at high latitudes. One of its key experiments, the Moon Impact Probe, detached and crashed into the surface, demonstrating India's capability for precise lunar targeting. NASA's Lunar Reconnaissance Orbiter, LRO, launched in 2009, has been one of the most transformative missions in modern lunar science. Equipped with high-resolution cameras, laser altimeters, and radiation detectors, LRO has mapped almost the entire Moon at resolutions fine enough to see the Apollo landing sites, the rover tracks, and even individual footprints. Its data has been crucial in identifying potential landing sites for future missions and in understanding the distribution of resources, especially near the poles. Launched alongside LRO, the Lacrosse impactor targeted the Cabeus crater at the lunar South Pole, ejecting a plume of material that confirmed the presence of water ice in significant quantities. China's Chang'e program has been a major driver of recent discoveries. Chang'e 3 in 2013 marked the first soft landing on the Moon since 1976, deploying the U-2 Jade Rabbit rover, which conducted geological surveys and tested equipment for long-term surface operations. Chang'e 4, launched in 2018, achieved a historic first, landing on the far side of the Moon. This region, shielded from Earth's radio noise, is of great interest for both geology and radio astronomy. Chang'e 4's rover, U-2 has been exploring the Von Karman crater in the South Pole, Aitken Basin, one of the oldest and largest impact structures in the solar system, providing valuable insights into the Moon's deep crust and mantle materials. India's Chandrayaan-2 mission in 2019 placed an orbiter in lunar orbit that continues to return high-quality data, though its lander and rover were lost during descent. The mission has mapped variations in the Moon's exosphere, studied mineral compositions, and continued the search for water ice. Meanwhile, private companies have also begun planning lunar missions, supported by NASA's Artemis program and the Commercial Lunar Payload Services Initiative, signaling a shift toward a more commercialized and cooperative model of exploration. One of the major themes of modern lunar research is resource mapping. Scientists are keenly interested in identifying deposits of titanium-rich basalts, which could be used in advanced manufacturing, and quantifying the extent of water ice reserves at the poles. The mapping of permanently shadowed regions, PSRs, has revealed that they may act as cold traps, preserving volatile compounds for billions of years. These areas are among the top targets for future exploration because they could support sustained human presence. Another focus is understanding the Moon's interior and geological history. Missions like GRAIL, Gravity Recovery and Interior Laboratory, launched in 2011, have mapped the Moon's gravitational field in extraordinary detail, revealing its crustal thickness variations, ancient impact basins, and signs of a complex thermal evolution. Combined with mineralogical studies from orbiters, these data help reconstruct the Moon's volcanic history and the processes that shaped its surface. Remote sensing has also uncovered unexpected phenomena, such as the presence of small-scale magnetic swirls on the surface, like those at Reiner Gamma, which seem to deflect the solar wind and create unusual space weathering patterns. The origin of these swirls remains uncertain, making them a subject of active investigation. Today, modern lunar research stands at the threshold of a new phase. The Artemis program, led by NASA with international partners, aims to return humans to the Moon in the coming decade, focusing on the South Polar region. This return will be deeply informed by the findings of recent robotic missions, the precise maps of LRO, the water detection from Lacrosse and Chandrayaan-1, the mineral data from Kaguya, and the geological context from Chang'e rovers. These combined results create a detailed, three-dimensional picture of the Moon that Apollo-era planners could only dream of. The Moon is no longer viewed solely as a place to visit and leave, but as a strategic location for science, resource utilization, and as a stepping stone for deep space exploration. The combination of robotic missions, satellite mapping, and targeted landings has transformed our understanding from a patchwork of Apollo landing sites to a comprehensive, global perspective. The story of modern lunar research is one of persistence, technological innovation, and an ever-growing recognition that the Moon holds the keys not only to our past, but also to our future in space. From the moment life emerged on Earth, The moon has been more than a distant celestial ornament. It has been a subtle but constant force shaping the rhythms of our planet. Its gravitational pull, working in tandem with the sun's, drives the tides, creates predictable cycles of light and darkness, influences the behavior of animals, and may even touch upon the internal clocks of human beings. While these effects often operate quietly in the background, they have been deeply woven into the biological, ecological, and cultural patterns of life for billions of years. The most obvious and scientifically measurable influence is the tides. The moon's gravity pulls on Earth's oceans, causing them to bulge toward it, while a second bulge forms on the opposite side due to centrifugal force as the Earth-Moon system rotates. As the Earth spins, different coastlines pass through these bulges, creating the familiar rise and fall of water levels. The sun also contributes to tidal forces, but the moon's proximity makes its effect stronger. When the sun, moon, and Earth align during new and full moons, their combined pull produces spring tides, exceptionally high and low tides. When the sun and moon are at right angles relative to Earth, the forces partially cancel, creating neap tides, with smaller differences in water levels. These tidal cycles are more than curiosities. They are engines of life. In coastal environments, countless species depend on the rhythmic flooding and draining of tidal zones. For example, certain crabs and shellfish time their reproductive cycles to spring tides, ensuring their eggs are carried out to sea. Some fish migrate into estuaries during high tides to feed or spawn, retreating when the water ebbs. On rocky shores, algae and invertebrates have evolved to withstand periods of exposure and submersion, their lives synchronized with the moon's gravitational rhythm. Beyond the shorelines, the moon's light also plays a role in regulating biological activity. Before the invention of artificial lighting, moonlight was the brightest natural illumination available at night. Many nocturnal animals have adapted to its presence or absence. Predators such as owls or large cats may hunt more actively during brighter nights, when prey is easier to spot. Conversely, prey animals like certain rodents or insects may reduce activity during full moons to avoid detection. This phenomenon, known as the lunar phobia effect, has been documented in several species, showing that even light from 384,000 kilometers away can influence survival strategies. For marine life, the combination of moonlight and tides can create intricate behavioral patterns. Coral reefs, for instance, often synchronize mass spawning events with specific lunar phases. These reproductive bursts, involving the release of eggs and sperm into the water simultaneously, may be timed so that currents carry the offspring away from predators. The exact mechanism by which corals sense lunar cycles remains unclear, but it likely involves both gravitational and light cues. Similarly, certain species of sea turtles hatch from eggs buried in sand and instinctively crawl toward the ocean, often guided in part by the reflection of moonlight on the water's surface. Migrations in some animals also appear tied to the moon. For example, the palolo worm, found in the Pacific, times its reproductive swarming to the last quarter of the moon, ensuring optimal currents for dispersal. Even large mammals like wildebeest and caribou have migration patterns that sometimes align with lunar cycles, possibly because of subtle ecological cues influenced by tides and moonlight. Humans, too, have been shaped by the moon's cycles, though the evidence is more complex. In ancient societies, the moon's phases were crucial for tracking time, planning agricultural activities, and scheduling cultural or religious events. The lunar month of roughly 29.5 days formed the basis of many early calendars and still underlies the timing of various festivals today. Some researchers have explored possible links between lunar phases and human biological rhythms, particularly sleep and mood. Studies have produced mixed results. but a few suggest that during a full moon, people may experience slightly shorter sleep duration and reduced deep sleep, even in environments shielded from moonlight. This raises the possibility of an innate, perhaps evolutionary, sensitivity to the moon's cycles. Another area of interest is the relationship between the moon and reproductive biology. The average human menstrual cycle closely matches the length of the lunar month, and some anthropologists have speculated that early human fertility patterns might have been synchronized to lunar phases, particularly before artificial lighting altered nighttime environments. While modern lifestyles and electric light have disrupted any such synchronization, the cultural association between the moon and femininity persists across civilizations, from the Greco-Roman goddess Selene/Luna to the Chinese goddess Chang'e. The moon's influence extends to climate and long-term planetary stability. By exerting a stabilizing torque on Earth's axial tilt, the moon prevents extreme variations that could cause chaotic climate shifts. Without it, Earth's tilt might fluctuate widely over time, leading to severe changes in seasonal patterns and possibly disrupting the evolution of complex life. This stabilization has indirectly shaped ecosystems, migration patterns, and even the emergence of agriculture, as a relatively stable climate allowed human societies to develop long-term food production. In more subtle ways, the moon has influenced human navigation and exploration. For millennia, seafarers used the moon's position, along with the stars, to plot their courses. Coastal communities learned to read the tides for fishing and trade, embedding lunar knowledge in oral traditions and practical skills. In Polynesia, navigators memorized the rising and setting positions of the moon at different times of the year to guide voyages between islands. While the moon's gravitational pull is the dominant driver of tides, it also influences Earth's atmosphere. Research suggests that lunar gravity can create slight fluctuations in atmospheric pressure and wind patterns, which may, in turn, affect weather on very short timescales. Though these effects are subtle compared to other climatic forces, they are measurable and contribute to the complex interplay of factors shaping Earth's environment. In the modern era, the moon's influence remains relevant in unexpected ways. Tidal forces affect the distribution and mixing of ocean waters, which in turn influences global heat circulation. This has implications for climate science, as accurate climate models need to account for tidal mixing driven by the moon. The possibility of harnessing tidal energy for sustainable power generation is another way humanity may continue to benefit from its lunar companion. The moon's impact is therefore multi-layered: gravitational, ecological, cultural, and perhaps even physiological. It is a force that can shape the migration of tiny worms and the spawning of corals, influence the hunting patterns of predators, guide the journeys of ancient sailors, and perhaps still whisper to our internal clocks. Its constancy in the sky has provided a foundation for measuring time, predicting natural events, and developing myths that frame human understanding of the cosmos. What is remarkable is that all of this stems from a relationship born billions of years ago in the violent aftermath of planetary collision. Since then, the moon has acted as both a stabilizer and a signal, a clock in the heavens whose influence ripples through ocean tides, animal migrations, and human cultures. While artificial lighting, global travel, and modern technology have dulled our immediate dependence on lunar cycles, they remain embedded in the deep structure of life on Earth. Even now, when we look up at the moon, we are seeing not just a distant rock, but a force that continues to shape our planet in ways both grand and subtle. For all its familiarity, the moon remains a place of enigmas, an object humanity has studied for thousands of years and even visited, yet one that still hides unanswered questions. Among the most intriguing are reports of unusual phenomena, strange lights, sudden flashes, and surface anomalies that defy easy explanation. These mysteries have sparked debate among scientists, inspired myths, and fueled speculation ranging from plausible geological processes to the realm of science fiction. One of the most enduring puzzles is the phenomenon of transient lunar phenomena, TLPs, brief flashes, glows, or color changes on the moon's surface reported by observers for centuries. Descriptions vary. Some report reddish glows lasting several seconds, others bright white flashes or mist drifting across a crater. The earliest credible record dates back to 1787, when famed astronomer William Herschel claimed to have seen 3 luminous spots on the moon, which he interpreted as volcanic eruptions. Since then, hundreds of reports have been compiled, with sightings coming from both amateur astronomers and trained observers. Modern explanations for TLPs range from meteorite impacts producing brief flares, to sunlight glinting off freshly exposed rock, to the release of gases from the lunar interior that reflect sunlight differently. While the moon is considered geologically inactive today, data from the Apollo seismometers revealed occasional moonquakes, suggesting that stresses in the crust could still cause minor surface disturbances. Some scientists propose that such quakes might release trapped gases, possibly producing visible effects. More recently, high-resolution monitoring from telescopes and lunar orbiters has confirmed small impact flashes, particularly during meteor showers, lending weight to the idea that at least some TLPs are caused by ongoing bombardment. Another category of lunar mystery involves lunar horizon glow, a faint light sometimes seen just above the moon's surface before sunrise or after sunset, reported by Apollo astronauts and observed by some robotic probes. This glow is thought to be caused by electrostatically charged dust particles being lifted above the surface by interactions with the solar wind. Because the moon has no atmosphere to damp such effects, fine dust can cling stubbornly to equipment and may even levitate under certain conditions. This process remains an active area of study, not only because it affects how we understand the moon's environment, but also because it poses challenges for future lunar exploration, as dust can be abrasive and damaging to machinery. The far side of the moon, forever hidden from Earth's view due to tidal locking, also holds its share of intrigue. When the Soviet Luna 3 spacecraft first photographed it in 1959, scientists were surprised to see a surface dramatically different from the near side, heavily cratered, with very few of the dark maria that dominate the side we see from Earth. The reasons for this asymmetry are still debated. One leading theory suggests that the crust on the far side is thicker, preventing lava from flooding low-lying basins in the same way it did on the near side. How this difference arose is uncertain. It may be linked to early tidal heating or to a massive ancient impact that affected only one hemisphere. Occasionally, anomalies have been reported in lunar photographs, objects or shadows that seem unusual. While most can be explained as optical artifacts, camera glitches, or tricks of light and perspective, they often capture public imagination. The so-called lunar towers, or glass domes, claimed by some fringe theorists are almost certainly image compression artifacts or geological features seen under unusual lighting. NASA and other space agencies generally attribute such anomalies to known processes, though the persistence of speculation reflects how strongly the moon invites curiosity and mystery. Even more controversial are claims of unusual sounds recorded by Apollo astronauts, described as space music heard in their headsets when orbiting the far side of the moon, outside of radio contact with Earth. These sounds were later explained by engineers as interference between spacecraft communication systems, but the story remains a favorite among conspiracy enthusiasts. The moon's magnetic anomalies are another subject of scientific interest. Although the moon has no global magnetic field today, certain regions, such as the Reiner Gamma Formation, exhibit localized magnetic fields. These swirls appear as bright, looping patterns on the surface, visible in optical images and accompanied by measurable magnetic signatures. Their origin remains unclear. Some scientists suspect they formed when cometary impacts deposited magnetic material, while others suggest they result from variations in the moon's crustal composition and ancient magnetic activity. Understanding these anomalies could offer insights into the moon's early history and the processes that shaped its surface. Another persistent puzzle is the distribution of water on the moon. For decades, the moon was considered bone dry, with any water ice confined to permanently shadowed craters near the poles, where sunlight never reaches. However, recent missions such as India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter have detected signs of hydroxyl and possibly molecular water across much of the surface, even in sunlit areas. How this water is formed and preserved remains uncertain. Possible sources include comet impacts, interactions between solar wind particles and lunar minerals, or deep interior reservoirs exposed by impacts or volcanic activity. Meteorite impacts themselves raise additional questions. The moon's lack of atmosphere means every rock that strikes it leaves a mark, yet some craters appear much fresher than expected, suggesting that significant impacts may be more frequent than previously thought. Continuous monitoring from Earth-based telescopes and orbiting spacecraft has shown that the moon is still an active target in the solar system's ongoing bombardment, which has implications for understanding impact risks to Earth as well. Adding to the list of curiosities are reports of unusual color changes on the moon's surface during certain eclipses. While the reddish hue of a lunar eclipse is well understood, caused by Earth's atmosphere scattering sunlight, some observers have noted greenish or bluish tints at specific locations. These may be caused by differences in surface composition interacting with refracted light, but the variability of these colors keeps them in the realm of ongoing study. Despite modern instruments and high-resolution imagery, the moon's mysteries persist partly because many of these phenomena are fleeting and difficult to observe consistently. A flash lasting a fraction of a second, a faint glow just before sunrise, or a rare color shift during an eclipse all require careful documentation to study scientifically. This means that for every confirmed explanation, new questions often arise, keeping the moon an active subject of both professional research and public fascination. In the end, these mysteries, whether rooted in geology, space weather, or human perception, remind us that the moon is not a static, dead world, but a dynamic environment still influenced by cosmic forces. It is a place where dust can rise without wind, where light can flicker unexpectedly, and where the surface tells a complex story written over billions of years. For scientists, each unexplained event is an opportunity to refine models of lunar processes. For the rest of us, they are a reminder that even our nearest celestial neighbor retains its secrets. As our exploration deepens in the coming decades, we may find that the moon's most intriguing surprises are yet to be discovered. The moon's future is increasingly seen not as that of a passive celestial body to be merely studied from afar, but as an active participant in humanity's next great chapter of exploration and development. Once regarded primarily as a stepping stone in the space race, it is now recognized as a strategic asset, scientifically, technologically, and economically. The decades ahead may transform the moon from a silent witness in Earth's night sky into a hub of human activity, a source of valuable resources, and a gateway to the deeper solar system. One of the most significant drivers of renewed interest is the possibility of permanent or semi-permanent lunar bases. Such bases could serve multiple purposes, as research stations for studying the moon's geology and its history, as testbeds for life support systems, habitats, and energy infrastructure needed for deep space exploration. and as staging points for missions beyond Earth. NASA's Artemis program, the European Space Agency's concepts for an international lunar village, and China's International Lunar Research Station plans all envision modular habitats on or near the lunar surface within the next few decades. These bases would likely be located near the lunar poles, where permanently shadowed craters may contain water ice and nearby ridges receive nearly continuous sunlight for power generation. The presence of water ice changes the moon's role dramatically. Water is not only essential for human survival, but can also be split into hydrogen and oxygen to produce rocket fuel. This means that a lunar base with water processing capability could refuel spacecraft, reducing the need to launch heavy fuel loads from Earth's deep gravity well. In practical terms, this could make the moon a refueling depot for missions to Mars or even the outer planets, drastically lowering mission costs and increasing flexibility. Beyond water, the moon may hold valuable resources such as rare earth elements, titanium, and particularly helium-3. Helium-3 is a light isotope of helium that is extremely rare on Earth, but relatively abundant in the lunar regolith, having been deposited over billions of years by the solar wind. It has been proposed as a potential fuel for future nuclear fusion reactors, offering the promise of enormous energy output with minimal radioactive waste. While commercial fusion using helium-3 remains a technological challenge far from realization, the idea adds to the moon's strategic allure. Countries such as China have explicitly mentioned helium-3 in their lunar exploration goals, and private companies are also considering its potential economic value. The moon's low gravity, about 1/6 that of Earth, gives it another advantage as a base for exploration. It is far easier to launch spacecraft from the moon than from Earth. This has led to proposals for using the moon as a launch platform or spaceport for deep space missions. Spacecraft assembled and fueled on the moon could depart with far less energy expenditure, enabling larger payloads or more ambitious missions. Some concepts envision mass drivers or electromagnetic launch systems that could hurl cargo from the lunar surface into orbit without the need for chemical rockets, further reducing costs. In addition to being a physical springboard, the moon offers unique scientific opportunities that could shape the future of astronomy and planetary science. The far side of the moon is permanently shielded from Earth's radio noise, making it an ideal location for building radio telescopes to study the universe at wavelengths inaccessible from Earth. Such an observatory could probe the early universe, detect faint signals from distant galaxies, and even search for signs of extraterrestrial intelligence without interference. The lunar surface also preserves geological records from the early solar system, offering scientists an unaltered archive of cosmic history that could answer fundamental questions about planetary formation and Earth's own evolution. International cooperation will likely play a major role in the moon's future. Just as the International Space Station became a platform for collaboration between nations, a lunar presence could unite spacefaring countries in shared infrastructure, research, and governance. However, the moon's resources and strategic advantages also raise concerns about competition and geopolitical tension. The 1967 Outer Space Treaty prohibits any nation from claiming sovereignty over the moon, but it leaves room for interpretation when it comes to resource extraction and private enterprise. The coming decades may require updated international agreements to balance exploration, commerce, and preservation. Commercial space companies are already positioning themselves for a role in lunar development. Firms like SpaceX, Blue Origin, Astrobotic, and Espace are planning landers, cargo delivery systems, and infrastructure that could support both governmental and private activities. This commercialization could accelerate progress, reduce costs through competition, and expand the range of missions possible beyond purely scientific ones. The moon could host not only research stations, but also tourism ventures, with private citizens visiting its surface or orbit for unique experiences, an idea once confined to science fiction. Sustainability will be a critical factor in shaping the moon's future. Lunar dust, extreme temperature swings, and radiation from the sun and cosmic rays present serious engineering challenges. Long-term human presence will require robust solutions for shielding habitats, recycling air and water, generating power, and maintaining equipment in an environment that is both harsh and unforgiving. Innovative technologies such as 3D printing using lunar regolith could allow construction of structures directly on the moon, reducing the need to transport materials from Earth. Solar power systems, possibly combined with small nuclear reactors, could ensure continuous energy supply, especially at the poles. The moon's role as a stepping stone to Mars is central to many exploration roadmaps. Establishing operations on the moon allows astronauts, engineers, and mission planners to gain experience in off-world living under conditions similar to, but less extreme than, those on Mars. Lessons learned from lunar missions, such as dealing with isolation, communication delays, in-situ resource utilization, and autonomous maintenance, will directly inform the design and success of crewed missions to the Red Planet. At the same time, the moon itself could become a long-term destination, not just a waypoint. Over centuries, humanity might see the rise of permanent lunar settlements, perhaps even small cities, supporting mining, manufacturing, scientific research, and space transportation. In such a scenario, the moon would no longer be just Earth's companion, but a second home for humankind, a place where generations live, work, and explore the solar system. In cultural terms, the moon's future will continue to resonate with the same blend of wonder and ambition that it has inspired for millennia. The image of humans walking on its surface, building structures under its stark sunlight, and gazing back at the blue Earth will redefine our relationship with both worlds. As technological capability meets age-old curiosity, the moon is poised to become a symbol not only of human achievement, but also of our species' expansion into the cosmos. The next century will likely determine whether the moon remains primarily a subject of study and occasional visitation, or whether it becomes a vibrant hub of activity in its own right. The decisions made today, in engineering labs, government offices, and international forums, will set the course for its role in human destiny. In all likelihood, the moon will serve as both a mirror reflecting our progress and a gateway pointing us toward the stars. The question is no longer whether we will return, but how we will stay, thrive, and use its unique position to propel us into the broader universe. Good night.